So here's our next problem, and we're given the acceleration, which is not constant, is going along the path. So we're starting from A, measuring path length, and so here's the acceleration as a function of distance along the path. Here's the path, we know it, and so we're going to go 40 meters along the path, and the question says find the acceleration of B. All right, well, very simply, knowing from this, if we put S into here, 0.06 times 40, the tangential acceleration at B, if we just stick that in there, works out to 3.6 meters per second squared. Okay, that's simply 6 minus 0.06 times 40. So that's easy. What we need is the normal acceleration at B, which is, of course, say v squared over r. All right. Now, so we're going to need r. Okay. So B corresponds to, notice in the drawing, it corresponds to x. So we're going to need r. Well, we can get r in the now usual way. R at 30 is simply 1 plus. So here's y as a function of x. Take the derivative. That's 2 on 100. So we got 2x on 100 here. Then we have to square that and bracket to the 3 halves. Then taking the second derivative, we get 2 over 100. Of course, 2 over 100 is 1 over 50. Anyway, use your calculator, pump this out, you get 79.3 meters. All right. So we got the r, we need the v. And how in the world are we going to get that? Well, if you think about it, tangential acceleration, velocity, they're both tangential concepts. So here I have at, which is a function of position. Well, what if I were to integrate that with position? Well, this piece right here, at, is simply ds dt, dv dt, let's put that in there, that's what I want to do. It's dv dt, and then we had a ds. Well, what did we do before? We just moved that over here, and now ds over dt is a v, so we have a v ds, or v dv. Here we are, this is a v. ds dt is a v, and that. So we have at ds. If I add a ds, make that dv dt, move the t over, that gives me a v and a dv. There. So that's how we solve this. Integrate here, integrate here. So, integral, we're going 40 meters along the path, so 0 to 40. Okay, 6 minus 0.06 s ds, there, equals integral of, we're starting here, the velocity here is given at zero, as initially 0, so we should put that in there. So going from whatever going from 0 to whatever velocity we're at, v dv. All right, so when you integrate this, this gives us 6s minus 0.06 s squared over 2 equals v squared over 2, because the 0 is boring. And you evaluate this at 0 and 40. And again, the 0 is boring. So if you do that, solve for this, you wind up with v equals 19.6 meters per second. Stick s equals 40 in here, solve for v. And so when you do that, that gives you an is v squared on r. So we have 19.6 squared all over 79.3 equals 4.84. This would be meters per second squared. All right, you can finish this up directly. Magnitude of the acceleration, which is what we're asked for. At, we computed at, that was 3.6 plus 4.84, square that, to the 1/2, 6.03 meters per second squared. And there we are.